So far the downlink and the downlink frame structure. Now what about the uplink? In the uplink, as already mentioned by Christina, another transmission scheme is used, known as single carrier frequency division multiple access. What does this mean? First of all, we have seen that OFDM got advantages but also disadvantages. The major disadvantage of OFDM is the high peak to power average ratio, also known as crest factor. This is the result as this transmitted signal is the sum of all modulated subcarriers, and as some of them are in phase, high amplitudes are not avoidable. The high peak to average power ratio requires high resolution digital analog and analog digital converters, as well as very linear transmitter circuitry, as any nonlinearity will cause intermodulation distortion, raising phase noise, causing intercarrier interference, and out-of-band spurious radiation. This is already challenging in the downlink, where we do have no trouble in providing power or space for the design. On the terminal side, this is nearly an overkill. The goal for 3GPP was to select another transmission technique for the uplink that keeps the advantages of OFDM, which is multi-carrier transmission and therefore an efficient use of the available bandwidth, and combines this one with the advantage of a single carrier transmission, which is, compared to multi-carrier, the lower peak to average power ratio. As the name already emphasizes, this is achieved with single carrier FDMA. Now, how a single carrier FDMA signal is generated from a high-level perspective. First of all, there's another block in the signal processing chain. A discrete Fourier transform is performed on the data symbols after serial parallel conversion, which transfers them from the time into the frequency domain. Afterwards, there is subcarrier mapping as in OFDM and an IFFT to transfer the signal from the frequency domain into the time domain. After the parallel serial conversion, the cyclic prefix is inserted. The last two blocks are the same as for OFDM, so there's no difference to the downlink signal generation chain. The DFT precoding is the essential difference between downlink and uplink. So what does DFT do? Well, first of all, it is a mathematical operation, but compared to OFDM in a downlink, where each subcarrier carries just one specific modulation symbol, the DFT takes the symbol and spread this one over the available subcarrier. In that matter, each subcarrier carries a portion of superposed symbols, therefore single carrier FDMA is also referred to as DFT spread OFDM. So this picture visualizes the things we just learned very well. When we compare classical OFDM used in the downlink and single carrier FDMA or DFT spread OFDM used for the uplink, then we can say that in OFDM each subcarrier carries only information related to one specific symbol. This is indicated by the color used for the subcarriers, as you can see on the left-hand side of the graph. In single carrier FDMA, each subcarrier contains now information of all transmitted symbols. You can see on the right-hand side in the graph that each of the different subcarriers carries now a little bit red, green, blue, orange, and so on. With this means with performing a DFT precoding, we shift around the problem of high amplitudes due to subcarriers in phase. Now the question that comes up is how the subcarrier mapping is realized in the uplink. There are two possibilities, each coming with one advantage. First, we do have localized mapping. In localized mode, the modulation symbols are assigned to adjacent subcarriers as shown in the graph. As shown, this would give us the advantage of multi-user scheduling gain in the frequency domain. For localized subcarrier mapping, single carrier FDMA is named as localized FDMA. The other mode, user distributed subcarrier mapping. In that matter, single carrier FDMA is referred to as interleaved FDMA. In this mode, the modulation symbols are equally spaced over the entire bandwidth. The advantage of this mode based on the robust transmission of control channels and the support of high mobility of the terminal. Now the question is which of the two modes is realized within LTE, and the decision was that the localized mode fits better to the overall system requirements. Further, both modes are impacting the peak to average power ratio differently. Again, the goal of introducing single carrier FDMA in the uplink was to lower the peak to average power ratio, enabling an efficient power amplifier design for the device. This chart shows the complementary cumulative distribution function, which describes the probability distribution of the peak-to-average power ratio. The CCDF is displayed for OFDMA, so for the downlink, and for both modes of single-carrier FDMA, localized and interleaf FDMA. This data is taken from an article published in IEEE magazine back in September 2006, so in the very early days of LTE definition. The simulation uses a system with 256 subcarriers in a 5 MHz channel, where 64 subcarriers have been assigned to the user, which are in case A, QPSK modulated, and in case B, 16-QAM modulated. Further, pulse shaping was applied to the signal or not. In difference to 2G and 3G, there's no filter definition in LTE, means this is open to the design engineers. Just the defined in-channel requirements, for example modulation quality measured with the EVM, and out-of-channel requirements, adjacent channel leakage power ratio or spectrum emission mass, need to be passed by the transmitter design. In this simulation, a root raised cosine filter was used with a roll-off factor of 0.5. As we can see, the crest factor for OFDM is constant at around 12 dB, which is comparable to WiMAX, and it is independent from the modulation scheme and the used filter. This is different for single-carrier FDMA, especially for interleaf FDMA. For localized FDMA, which is the blue line, which is the mode which is used in LTE, the peak-to-average power ratio is in case of QPSK modulation around 8 dB and therefore 3 dB lower than OFDMA. For 16-QAM the difference is just around 2 dB. As already emphasized by Christina, LTE uses two modes: frequency division multiplex (FDD) and time division multiplex (TDD). The parameterization in the uplink is for FDD the same as in the downlink. The two different cyclic prefixes are used, normal and extended, giving 6 respectively 7 single-carrier FDMA symbols in the uplink. For TD-LTE, the usage of the uplink depends on the selected uplink-downlink configuration, where each configuration offers a different number of subframes assigned for uplink transmission. But the parameterization of those subframes is of course equal to FDD mode and depends on the selected cyclic prefix.